Welcome everyone. Today we are going to explore something that most of us never really see. It is a hidden layer where software meets hardware. Think about it. We click an app, it runs instantly. But how does our written code, probably in C, C++, or Python, actually talk to the processor? And that invisible bridge between software and hardware is built using application binary interface or interfaces. It also makes use of some rules related to memory alignment. These two might sound technical, but by the end of this session, you will see that they are just simple ways of keeping the system organized, compatible, and fast, no matter which computer we use. Let's start from the foundation. Imagine you and your friend speak two different languages. Now you will need a translator to communicate properly. And that's exactly what ABI does for the programs and hardware. An application binary interface, or known as ABI, is a set of rules that tells a compiled program how to run correctly on a specific computer. It decides how data is stored in memory, how functions pass information back and forth, and how programs talk to the operating system to get things done, like saving a file or printing a message. Once your source code becomes machine code, the ABI makes sure it can run smoothly, no matter which compiler or programming language you have used. So you can think of ABI as a universal translator between the program and the system. Let's look a bit deeper into what makes the ABI special. First, the ABI acts like a contract. This is a clear agreement between software and the system. It is like it says, here is how I will call a function. Here is how I will store the data. Here is how I will talk to the operating system. If everyone follow this agreement, programs from different developers written in different languages will still work perfectly together. Now question arises, what is the difference between API and ABI? Think of an API, like well known as application programming interface, as a handshake you can see, which defines how you write the code. Whereas the ABI, it is a handshake behind the scenes. It defines how the compiled binary behaves once it's ready to run. Every platform has its own ABI. A Linux program won't run just on Windows, even if the source code is identical. The reason being, they speak different ABI dialects. Now, stability is very, very important. A stable ABI means that even if you update your system or libraries, older programs will still work. It's like renovating a house without breaking the plumbing or wiring. Here, you are improving things without breaking what already works. And that's why software companies spend years maintaining the ABI compatibility. It's what keeps our system reliable. Now, let's move to another key part called memory. Every single piece of data in a computer lives at a specific address in memory. The way this data is placed and accessed, it can decide whether your program runs fast or painfully slow. So here you will require to understand Indianness. Let's talk about Indianness. Don't worry, it's pretty simpler than it sounds. Imagine writing a number, say 1234. You can either write it as 1234, which is a normal order, or 4321, which is a reversed order. Computers can store bytes in both ways. So these are the two ways. First is Little Indian. In Little Indian, it stores the smallest byte first, and this is used mainly by Intel x86 processors. Whereas other is Big Indian, stores the largest byte first, and this is used by some of the ARM processors. When two systems with different Indianness share data, they need to swap the byte order to understand each other properly. Next comes alignment. Imagine books arranged neatly on a shelf. Everything fits perfectly, and you can pick one quickly. But what if they are tilted or scattered? You waste time finding them. In computers, aligned data means a data is stored neatly in proper memory boundaries. If it is not aligned, the system may slow down or even crash. So alignment rules help the system stay fast and efficient. Now let's talk about how processors understand instructions. Different processors speak slightly different instruction languages. ARM processors use fixed length instructions, usually 32-bit long. It's like every sentence in a book having the same length, and that makes it easy to read and quick to decode. Intel x86 processors use variable length instruction, which ranges from 1 byte to 15 bytes. And this makes them compact and flexible, but a bit more complex to decode. And when it comes to addressing data, there are few methods. Like some of them are mapped here or addressed here. Let us say immediate addressing. The value is right there inside the instruction. Register indirect addressing. The address is stored in a register. Program counter relative addressing. The address is found by adding an offset to where the program counter currently points. And this helps make the code position independent. ARM keeps addressing simple and consistent, while Intel x86 uses more complex methods that allow flexibility but require more effort from the processor. So, when one function calls another, there are rules that keep the things organized, and these are called as calling conventions. They are like traffic rules for a function call. In ARM, like extended ABI, EABI systems, the first four parameters are passed through registers R0 to R3, which is fast. In Intel x86, parameters usually go through the stack, while in newer x64-bit systems, they use the registers too. The registers are divided into two groups. Caller saved, that is the calling function takes care of them, and callee saved, that is the called function takes care of them. And this prevents data from getting accidentally overwritten. When programs are linked and executed, the computers make sure every address points to the right function or a variable. It's like checking every street sign before driving. You must know where every road leads to. Every program that runs on your computer gets own little world of memory thanks to virtual memory. Virtual memory creates the illusion that every program has all the memory it needs, even if the physical memory, that is RAM, is smaller. It also isolates each program so one cannot harm another, like each app living in its own apartment. Memory is divided into small chunks called as pages, usually 4 KB each. The page table keeps track of where each virtual page is in physical memory. Modern systems like Intel x86 uses multi-level page tables for quick access. So paging and virtual memory together keep your program safe, organized, and running efficiently. Let's make it practical. Memory map files allow programs to treat files like memory. No need for slow read or write calls. It's like having shortcuts straight into the file's content. This is widely used in databases, video players, as well as the large applications. Shared libraries are another great invention. They are permitting or letting many programs share the same code instead of keeping separate copies. And this helps saving the memory, and making the updates is very easy now. If you fix a shared library, all programs using that shared library get the fixed instantly. To make this possible, internally they use position independent code. And this type of code doesn't care where it is in memory, it just works. It uses relative addressing instead of fixed memory addresses, and that makes it flexible and efficient. So Linux system follows a common set of ABI rules known as System 5 ABI, System V ABI. And these rules define how data types, functions, and binaries interact with the operating system. They keep programs consistent across different Linux versions and hardware types. ELF, the executable linkable format, is a part of this ABI. It tells Linux how to store and load executables, object files, and shared libraries. The ELF format supports position independent code, dynamic linking, and symbol resolutions for functions and variables. So together, System VABI and ELF form the foundation that makes the Linux software stable, flexible, and portable. Each processor family has its own personality. ARM, where focus is embedded, they are pretty simple, low power, and efficient. These are perfect for mobile devices, embedded systems, as well as the IoT gadgets. Whereas Intel x86 has a huge complexity. This is powerful, flexible, and backward compatible. It is great for desktops, servers, and performance heavy systems. Intel 386, a legacy, the first 32-bit processor in x86 family. It introduced multitasking, protected mode, and paging. These are all the essentials for modern operating systems like Windows and Linux. So in large multiprocessor systems, memory access speed isn't the same everywhere. And that's what we call NUMA, non-uniform memory access. Each processor has its own local memory. Accessing nearby memory is fast, but reaching another processor's memory is slower. So programs should try to use memory close to their processor whenever possible. When data is aligned properly, the processor's cache works efficiently. If the data is misaligned, the processor might need multiple steps to read it, and that slows the things down. So embedded systems demand perfect alignment. Even a small mistake can cause an error. Desktops and servers can handle small misalignments but may lose the performance. So good memory alignment is like keeping your desk clean. Everything is easier and faster to find. Now let's meet LLVM, a modern compiler framework that powers languages like C, C++, Swift, and Rust. LLVM stands for Low Level Virtual Machine. Though today it's more than that, it's a whole toolkit for building compilers. It converts your source code into an intermediate form called as LLVMIR, intermediate representation, which optimizes it and then creates a machine code for your target system. The LLVM data layout describes how data should be stored, which includes alignment, Indianness, and the ABI rules. This helps LLVM to generate correct, efficient, and portable code for any architecture, whether it's ARM, Intel, or RISC-V. Simply putting this, LLVM learns the accent of each computer and make sure your code speaks it fluently. So, what we have learned today, ABIs are the rule books that keep programs and hardware in sync. Memory alignment ensures that data flows smoothly and efficiently. When both work hand in hand, programs become faster, safer, and compatible across systems. Even though we never see these details on the surface, they are the reason your apps launch smoothly, your operating system stays stable, and your code runs in the same way on every computer. It is the silent teamwork between architecture and software and acts as the bridge that makes modern computing possible. Thank you.